dysfunctional vet with a discussion about measuring low flow streams. The formula is width times depth, and you want to average the depth, times distance divided by time, and you want to do 3 samples of the time, and then multiply by 0.85. That is to correct for the fact that surface flow is faster than what's actually in the water. So this is just a correction factor. The next fact that you need to keep in mind is that if you're measuring in feet, you want to measure in feet and do all your calculations in feet. If you're measuring in inches, you want to convert it to inches. If you're using metric, all your measurements, your width, your depth, your distance, all needs to be metric. I have a friend from Europe, and he was a bit perturbed by my use of standard because he is used to using metric. So with that said, we'll get on to the actual measurements now. This stream, as I told you, is extremely small. You can step right across it with no effort. The measurement in width turned out to be 9 inches. I took 10 measurements because the flow was so slow and it was so shallow, starting at one bank and going all the way across to the other bank. Both edges were about ½ an inch deep, and then it immediately dropped off to 1 inch, and it maintained that 1 inch all the way across the face. So I determined that 9 times 1 is 9. Now, if you were going to paint a wall and it was 8 by 10, you go 8 times 10 is 80 square feet. It's the same thing here. 9 inches wide, 1 inch deep is 9 square inches. Now I'm starting with inches, so all of my measurements are going to be in inches while I determine the flow of this slow flow creek. The next step is to determine how long it's going to take a stick to float 10 feet. Now, as I told you, this area was very hard to measure. It took repeated efforts to do it, and I was unable to successfully time this thing 3 times. I did get one test where the object floated free and made it all the way the 10 feet in the time. It would have been better if I could have done this 3 times, but again, the flow is so slow that the object wanted to float off to the side. So what I have now is I have my distance of 10 feet, my time in seconds, and what I have to do is convert those feet into inches. So I'm going to multiply my distance times 12. Since I'm using inches, all of my measurements from here on out will be in inches. So 10 times 12 is 120 divided by my time. The time it took for the object to float the 10 feet was right at 180 seconds. Now, as iffy as to whether it was 179 or 181, because the thing was barely moving. But when it finally first touched where the pin flag was, I went ahead and called time, and it's within a second, plus or minus 180. Not real accurate, but the flow is really slow. Now remember one other thing. When I went to survey where the dam is actually going to be built, and I measured down, I realized that a lot of this water that's coming out of the ground is being lost back into the soil, and that is further complicating things. It is not physically possible to walk in many of the areas where this thing is because the water has turned the soil into quicksand, and it's actually flowing through it. If you were to step in, you'd sink up to your knee, which happened, and when you get your foot out of the hole, it immediately fills up, and you can actually watch the water slowly clarify as more water is coming in and the muddy water is being sucked into the bank and the water is flowing. This little discovery of stepping into the quicksand explained the mystery of why there appears to be more water than what there is. The water's there, it's just not accessible. So let's move on to the actual calculation here. 180 seconds equals 3 minutes. So using the 180 divided by the 120, I come up with this 0.66. So that's my water that's moving by, but I now need to add a correction factor. So let's do that. I have my distance divided by time, 0.66. Now I multiply by the face area, width times depth, which was 9, and I come up with 6. You now multiply by a fudge factor of 0.85 since the surface is moving slightly faster than the body of water. And you come up with 5 cubic inches per second crossing the face of that 9 inches. The width of it, that 9 inches, is moving 5 cubic inches per second. Now keep in mind that that's across the entire surface area of that 9 inches. There's 5 cubic inches, and that's per second. The next thing we need to do is multiply that by 60 to find out how many cubic inches per minute are crossing that face that we're trying to get the water from and measure accurately. You have the 5.1 cubic inches transversing the 9-inch face every second. If we multiply by 60 to get the total amount of cubic inches per second, we come up with 306 cubic inches per minute going past that face of 9 inches where we were measuring, where we could actually see the water. As you know, there's 231 cubic inches in a gallon, so we divide by 231. We come up with 1.32 gallons of water per minute going through that creek. So we had to size the ram pump to accommodate the 1.3 gallons per minute. Again, there may be more water there, but if we can't access it, we can't use it. So we have to use that 1.3 gallons per minute to do the calculations on the ram pump. So what is our conclusion? Our conclusion is that in order to have a ram pump that operates, we have to drain the water from the reservoir that we're going to create by building the dam at a rate slower than 1.3 gallons per minute. The flow rate is a very interesting thing. You can pull these tables up on the internet. There's nothing scary about them, hard to find. But a gravity flow pipe of 1/2 inch will move about 1/2 gallon per minute. If we were to scale that thing up by 1/4 inch and the pump were to cycle a little bit faster than what we're anticipating, which is about once every 1.5 seconds, or about 40 cycles per minute. If it were to function a little bit fast for some reason, we would quickly drain our reservoir and the pump would cease, and you'd have to go out there and reset it and get it going again. So rather than do that, we're going to make sure that we don't run out of water by using 1/2 gallon per minute. And the actual amount that it's going to pump may vary, but based on a very small amount of water moving each time, it's estimated that this pump will move approximately 600 gallons per day. Again, this is off of a 1/2 inch pump with a 15-foot drop in elevation so that we get plenty of pressure coming down. If you do your research, you're going to find that you need a minimum drop of 18 inches. That's all well and good. However, the more pressure that's coming down, the more water you're moving on each cycle. Remember, you have a waste valve, so half of the water that's being pumped is being dumped right back into the stream. It's a necessary evil. The water wasn't being used prior to starting to pump, and now you're losing some of it. It's not a big deal, but it does work. With that said, I'm going to conclude this functional vet out. Thank you for watching. If you like my videos, please consider subscribing and share with other people to help grow the channel. Again, I don't ask anyone for money. I do all this stuff on my own dime. I know everybody's hurting, myself included, and I'm not going to put some kind of burden on someone for what I like to do anyway. Dysfunctional Vet out.